The next speaker is Ulrich from Cambridge University and talk about translocation events.
Great. Thank you very much for this very kind invitation. And I realize that I'm actually the only experimentalist in the speaker field, so I apologize for the lack of mathematics. However, I think we have interesting problems maybe to discuss here in these systems. I'm also not too sure, like the speaker before, if we have a lot of anomalous diffusion. I think we normally ignore the anomalous diffusion in our systems, but we are interested. But I'm a physicist by training, so I'm interested in looking at these things for sure. So I will tell you a little bit about, of course, one ingredient I think for many of these systems is that we have all out of equilibrium transport measurements. So we really apply energy to the system, and then I believe many things can happen, like life. Yes, so if you have an energy source, and all kinds of stuff happens. So this is what I find interesting. Yeah. So of course I didn't do the work. This is the typical experimental lab. There's a lot of people who contributed. I will talk about work that was started by Nick Bell, who's now a lecturer at UCL himself. And then I will also talk about work that was done by Philip Boscovich. He's now a postdoc at Oxford, and in Chicago, and Kai Chen, who's now a professor in China, and some other people. I always also will have a long-standing collaboration with some simulation people, and I would definitely emphasize Alexei Aximentiev and Urbana Champagne, because our systems are kind of complex, so we don't use a lot of analytical models, but have to use a lot of simplification. And I will also tell you a little bit why I found the first talk extremely exciting, because we also have a classification problem because we want to detect molecules, okay? So I always show this thing because, of course, I'm from the Cavendish lab just over the road, and there's this nice quote from Watson and Crick about DNA as the secret of life with a double helix. And I mean, the fundamental thing is that we use in this talk a lot is that we use the double helix to do something interesting for sensing. Yeah. So again, here's a nice photograph of the model that you can see in the Cavendish lab in the first floor. That they built. Just a quick reminder, the size of the molecules is 2 nanometers in width, and of course DNA can be very long. It's a double helix, so you see this nice right-handed animation here that you can find on Wikipedia. And then if you look at it and think about how this works, is that you have the Watson-Crick base pairing, where A binds to T and guanine binds to cytosine. So we understand this quite well now. You can model these energies, and this means that you can actually use DNA as a building material, because if you can synthesize DNA, you can make any shape almost that you want. Again, it's the challenge for all these kind of systems in biological sensing is, in the end, yes, we want to convert biological information into electrons, okay? So we need some way to get the sequence of the DNA molecule into a computer and then do something with the models that we have. Yeah, so this is basically one of the challenges. And why is this a challenge? Just to give you some idea, yes, so length scale of humans is 2 meters. Typical cell, we just saw this nice movies from the previous speakers, is around 20 micrometers. And a DNA molecule by diameter is 2 nanometers shorter. But however, if you now think about it, how much information we have per cell in our body, so we have 6 billion base pairs per cell. So we have roughly 40 trillion cells in the body. So if you look at one single DNA strand in our bodies, it's actually larger than most humans, yeah, in each cell. So, and of course, in the last years, with the advent of advanced sequencing technologies, it also became clear now, yeah, that the DNA in all our bodies is not the same in each cell, okay? So with more technology, you know, we find out that actually the DNA and the genome is actually more complicated than we thought, and this is, of course, also based on single cell technology. And this is kind of important, because in the end, if all the cells in all our bodies are all different, then you have a challenge, yeah, that you have to, if this is a state or important even, or if there's noise and fluctuation, it's washing these differences out, but this is all important then. So again, yeah, so just to give you some numbers, yeah, so if you have 2 meters of DNA per cell in your body, then you have roughly 16 times 10 to the 12 meters of DNA in each of our bodies, yeah. So of course, the ways some technology to read this information is, of course, challenging. And I don't know how much you know about DNA sequencing technology, but there's, of course, a revolution going on at the moment because there are now the next generation sequencing that was built by by Illumina Technologies, and is now the market leader. Was available since the early 2000s, and now there's a new, two new technologies on the block that use single molecule readout of DNA structures by basically employing enzymes, and one technique uses fluorescent readout. Okay, so you basically, the idea is very simple, that you have a polymerase here, that's the naturally derived enzyme that incorporates dye molecules into a DNA strand, and you, from the color of the dye, you can read which base it is. And the other technology is that was mentioned also from Professor Lyons, Oxford Nanopore Technologies. It's kind of nanopore sensing, and the technology here uses also an enzyme, but it's a bit different. So you directly convert the structure of the DNA into an electronic signal with ionic current that I will explain in a minute. Okay. However, the most important thing that I want to just give you, this is the one thing that you can take away from this talk, that all the commercially available applications now rely on enzymes, and enzymes have some kind of, it's very hard to make them work faster. Okay, so most of these enzymes, the rule of thumb is they have stepping times of 1 millisecond per base. Okay, this of course slows you down a lot because, again, as I said, all the commercially available techniques to use enzymes for DNA sequencing. Typical rate is 1 milliseconds per base pair. So just with one single enzyme, yeah, to read one piece of DNA in our cells would, of course, take 3 times 10 to the 6 seconds. Was quite long. Of course, the idea is what these people do now. You multiplex the system, yeah. So you have many of these enzymes working in parallel, and then, of course, you can speed it up. But if you now have this task of actually scaling up to all the molecules in all our body cells, then you actually would now with a single enzyme, this would take 3 times 10 to the 18 seconds. You can think about how many years this takes. It's not really feasible. So the question is now, we have, however, a lot of information. So can we actually use a trick to make everything read fast? And this is what I want to talk to you a little bit about. And then we also come to the classification problems that we have to convert information into classified problems. Okay, so the idea that we have is the following. Yeah, so we don't want to read the single base because we know the sequence of our target molecule. So if you assume we have a DNA molecule, and again, as you know, that all our different genomes are 99% the same. So what you can also do, you might not have to read every single base, but what you can, if you, for instance, want to know how many RNA molecules of a certain type or DNA molecules are available there, and this, of course, could be also viral DNA or bacterial DNA, whatever. What you could do, you could use our knowledge of Watson-Crick base pairing to design a barcoded molecule. Yeah, so you make everything larger. So it makes it easier to read. You can maybe avoid the enzymes. It slows everything down and speeds the readout process up by orders of magnitude. And then if you have a factor of 1,000 or so, and of course, then you have a technological advantage that might be useful. Okay, so what's the idea? So what we are doing in my lab, we are having a target molecule that we want to read. It's not drawn to scale, the real molecules are longer. So then we design this kind of pool of short DNA strands that bind in a certain pattern along this molecule. Okay, so this, of course, now looks like an unstructured molecule. But now what we can do is we can actually ask the company or do it ourselves in the lab, label some of these molecules with markers. Yeah, these red balls can be dye molecules, a protein, another DNA structure, an RNA structure, whatever you want. Yeah, it could be a polyacyclic glycan molecule, whatever you can put on there. Now if you have this pattern, because you know the sequence of the target molecule, you can now distribute this pattern and make a barcoded molecule in these kind of systems. And the nice thing about this is an extremely simple process, because all what you have to do is you have to take your DNA molecules, a pool. You can order this for very cheap now from commercial companies. You heat everything up, cool it down, and then you have the barcoded DNA molecule. And again, the idea here why we are faster, we don't rely on enzymes. Okay, so there's no enzyme in the following things. So now I wanted to tell you how our sensing technology works, because as I said, we want to convert biological data into electronic data. Okay. Because computers are pretty fast and we can do things with it. Yeah? So the idea is extremely simple, and it's the following. Okay, so what we do is we make a small hole in the membrane that doesn't let water or ions through, and then we put this whole thing into a water-based solvent. We use aqueous solutions normally because this is nice for biological molecules. Then we add the salt, so we just can use table salt. We use lithium chloride. This has technical reasons that I don't want to go into here. And basically now you apply voltage over this small nanopore, and what this means that the ions are forced to move through the small constriction here, okay? And this defines the kind of sensing volume that anything that goes through there changes the ionic flow pattern, and this is again kind of a diffusion to capture process because the ions of course have to diffuse through the nanopore mouth and then go through. And this actually gives you a kind of a sensing volume that is indicated here by this red circle, red ellipse, okay? Okay, so now how do we make our nanopores? I just want to quickly show you the idea here. So this is our molecule here. We have a nanopore here sitting at the top of this kind of glass capillary. This is an SEM image, and the diameter of these pores in our lab is between 3 nanometers and 50 nanometers. So I already can tell you now, we don't sequence DNA. What we read this barcoded molecules, okay? So and again, this is where it's faster than the established sequencing technologies, and there we gain our advantage in speed. So if you look at this a bit to scale, so a DNA molecule is pretty stiff polymer with a persistence length of 50 nanometers, so it's hard to bend. And this one is actually drawn to scale. So the idea is really that you have a molecule here going through the nanopore, and again, this is roughly drawn to scale. So the black line is representing 2 nanometers, and we are sucking it into the system. And maybe here to just say how this looks in real life. So these are, you can easily label these DNA molecules with fluorescent markers. And just to show you that this is a diffusion to capture process, here's a video that we took a long time ago. So again, these bright dots, I hope you can see them on the screen, dancing around. These are DNA molecules that are fluorescently labeled, okay? And then we have a nanopore sitting roughly here where my laser focuses, and you can see if you follow some of these bright dots, they are diffusing to the entrance and then are sucked in, and this is a very fast process. Yeah, you see some of them disappearing one by one in this kind of in the nanopore. Yeah, so the nice thing about this is it's a single molecule technique, so you can read single molecules. Okay, so we have information about the whole distribution of molecules, so we can really see single molecules. It's a very powerful advantage of the technology. And you can also directly convert the molecular structure into electronic signals, because all what this is here, we have an ionic current amplifier that then translates the structure into an electric signal. So how does these systems look like? So this is just, again, to show you why we are dealing with fluctuations, why it's actually interesting to deal with noise and think about fluctuations and also diffusion problems here in the systems. If you look at a typical trace here, this is a current, it's a function of time. And each of these dips here that you can see here is one DNA molecule going through our nanopore, okay? So the interesting thing again here, this is times of seconds, yeah? And if you now zoom in to one of those things, you can actually see here that the relative current change is going down, so the DNA blocks the ions, so you can actually read off the structure in the system. So this is now an unstructured molecule. I just want to show you how the data looks like, yeah? So we have a lot of data, a lot of these molecules go through per second, so we have extremely fast single molecule readout, what is kind of important, okay? So then, of course, we have parameters. You can now characterize these kind of events by some kind of, okay, how long does the molecule stay in my nanopore? What is the typical blockage current? What is the noise level here? And this is actually something that Oxford Nanopore uses to determine the sequence. And again, I would just, if you have questions about this, we can also discuss this over lunch. So coming back to our idea now, so the following is the idea again, yeah? So we have now a molecule, we don't want to read the sequence, but what we actually want to read is the barcoded structure along this molecule, okay? So again, we convert the structure into a current time course here, and this is yeah, very sophisticated simulation, as you can see, how the molecule goes through. Of course, it's a bit more complicated than this, but fundamentally you see here that we can now read off, yeah, the ionic current signal is in principle acting like a microscope for the structure that we have. Yeah, so we convert again the molecular structure into an electronic structure that's easy to digitize and measure. Okay, and then the nanopore is like a readout for and a microscope for DNA, RNA, DNA structures. They can also be proteins, whatever. As I said, this red balls can be anything. It can be a polymer, can be a protein, or whatever structure makes a difference in the ionic current. Okay, and then of course we have the time now, because the only difficulty with our technology is that we actually measure current as a function of time, so we don't have a direct length measurement. And this is actually one of the issues that we have to solve with classifying elements, because we of course have only a time signal and we have to make assumptions about the lengths along the molecule here in the system. Yeah, because of course to identify the labeled molecule, we need to know where the labels are relative to each other, maybe relative to the end. Yeah, so this is a fundamental problem. And by the way, this is a problem that also Oxford Nanopore had in the beginning when they tried to sequence, and the solution they of course have is that they have this helicase sticking on top of the pore and ratcheting the DNA slowly through. Okay, so they have the same problem like we have, but they solved it by using a molecular machine that slows the DNA down. Okay, so again, this is a typical measurement. So normally our molecules are not fluorescently labeled because we don't want to do this, yeah, because it's kind of another chemical step. It's just a reminder, this is a diffusion to capture process, so everything is fluctuating. We are working at room temperature, the noise is large. So the fundamental problem that we have to deal with always is how can we convert time into distance. Again, why is this important for us? Because the labels and the barcodes, of course, yeah, if you don't know how time relates to distance, we can't identify the molecule. So the fundamental problem is how can we do this, okay? The other challenge, of course, you have a lot of different DNA molecules. You might have a lot of different targets depending on what you want to do. You might also use this kind of way for data storage, by the way. Yes, you can make this kind of into a string of bits. And then, of course, the question is always which data do you read? And this is fundamentally a classification problem, yeah, because we have all these kind of different events, and I will show you in a moment how this looks. And the question is now, which class of event does this molecule belong to? And again, this is why I like the first talk very much. So the question for us always is, which event is an outlier? Is it a real outlier? Is it a rare event? Is it something that shouldn't be there in the sample? Yeah, and to just show you, maybe this is an old video from almost 10 years ago. So we made this kind of in a system where we have this barcoded molecular section where we have a barcode here, and barcode is digital barcode here. So one of these markers here is a digital 1, so a small peak. And if you don't have 1, there's a 0. Okay, so it's very easy, it's extremely simple to encode. Yeah, so you have, for instance, you have this barcode section 1, 0, 1, 1, 1. Okay. So again, as I told you, we have some problems with ends of molecules and all this kind of things. This is why we only use 3 barcodes here to have 8 different molecules in this mixture. Yeah? So you see the barcodes here are 0, 0 to 1, 1, 1. Yeah? So we have 8 different molecules. This is a mixture of molecules, and then now we're passing this through the nanopore. And I hope the video runs now. Let me see. Probably not. Okay. Yeah. So what you see here now, how the different events look like in the system. Yeah, so we have a software. Again, this is relatively simple to do because we don't use all the data, because we throw a lot of data away. And again, I'm happy to talk about these challenges in the system a bit more over lunch. But fundamentally, we know now we have 8 different barcodes, 0, 0, 0 to 1, 1, 1. And they all encode for different binding sites for a certain protein that doesn't matter here what it is for, but fundamentally this is basically a system where we want to classify which barcode is it and which protein is there or not. And this could also be a certain sequence on a DNA molecule that is labeled with a certain protein, CRISPR-Cas9 or whatever. Yeah, but just to show you what the idea is. So the idea now is that we have thousands and thousands of these events, and we have to sort them into bins and say, okay, does this one that looks a bit funny belong into the 1, 1, 1, 1 category or in the 0, 1, 1? Do I miss a 0 because the molecule might actually change its speed a little bit during the translocation? And just to illustrate this, yeah, if you look at carefully in these kind of things at the beginning, when the video was a bit slow, you see that some of them, sometimes the peaks looks a bit distorted. Yeah, sometimes you see here, well, is it a 0 here? Is it something that is slower? So you have to always make these kind of decisions. Which kind of event do you have here? Okay. Just to give you another example here, this is now a later paper where we now actually mix 16 different barcodes together. So just, don't look too much into these events. Anyway, but fundamentally, we have, of course, good signal-to-noise ratio. But if you look at the events that we classified to be the same, you see that they can be quite different. Okay. From each other, and this is again one of the biggest problems that we have is how can we be sure what is in there and how to do this in the best way. We also played around with machine learning, but I'm not sure that we really have the best way yet. Okay. However, there's another problem. I told you fundamentally what we always want to do, we want to convert time signal into length. Okay, so the question is if there's some interesting physics. Now we come to the talk title, that we can now do some polymer physics in nanopores, because what we can of course now do, if we can design molecules where we know how they look, we can in principle make a ruler to convert our time signal into a length signal unambiguously, because if we know where the peaks are, yeah, we can now ask our question, okay, is the molecule going smoothly through the nanopore? Does it stop? Yeah, how does it work, and can we actually correct for this? Okay. Just a quick reminder, yeah, so these are long polymers, yeah, the typical molecules we're working with are several micrometers long, and so it's a thin string of 2 nanometers, so you have huge aspect ratios, you have Brownian motion of these polymers. This is how I attempt to show Brownian motion and how you get these kind of fluctuations in the polymers. And the annoying thing is, of course, that all our time scales in these systems, if you pull very rapidly on a polymer, you don't give it time to relax. Again, Oxford nanopore, that's the DNA going through relatively slowly with stepping times of 1 millisecond. Then the molecule has so much time to average over all configuration that you don't have to worry about many of these details we are worried about, because of course, if you measure faster, yeah, you might get a mixture of time scales, but also makes the modeling much harder. Because fundamentally, you can calculate how long does it actually take a long molecule that we have to equilibrate to a new position, and this is called Sim time. It's basically scaling with the square root of n to the power of 3, so 3/2 roughly, and this can be several milliseconds for these molecules, and I told you we suck through these molecules in milliseconds, so everything is mixed. Yeah? So if you look at the translocation time as a function of DNA length, in all the solid-state nanopore papers, yeah, you are actually in the regime where you have mixing between the timescales of the translocation and the equilibration. Okay, I hope it's fine. Okay, so this is a fundamental problem here in the system. So, and this also makes the modeling hard, maybe also interesting for polymer scientists, but fundamentally we have a mixture of length time scales, and this is always hard for analytical theory. So this is a non-equilibrium process as well, so it's a non-equilibrium statistical process that does not allow for polymer relaxations. You will see all kinds of different behavior in the systems. Okay, so now I told you, okay, how can we look at what is going on here? Also, it's quite interesting because it's not out of equilibrium. We have single molecule resolution, so we can really look at velocity fluctuations on a single molecule length scale. Okay, so what is our test bed now? So we made these rulers, okay, so that we called, this is just a long DNA molecule where every 1,000 bases or so, we have one of these peaks, yeah? So we know exactly these distances. How we make these peaks is just basically DNA structures to have no problems with proteins, but again, this is a detail not so important, but fundamentally now what we do, we take this nanopore in our membrane, we apply the voltage, and we pull our marker DNA through, and I hope you can see this. Here are the markers. Okay, this is again drawn to scale. The nanopores are usually 5 to 10 nanometers, so 10 nanometers in this work. So it's kind of 5 molecules fitting in here next to each other. Yeah, so it's drawn to scale with the length as well. And then you see the markers here, they're in red. And the signal, and this is now real data, it's not an animation anymore. This is really our signal to noise ratio. This is another thing that I would like to say here, because we have a kind of possibility to make large signal to noise, much larger signal to noise signals than Oxford nanopore. We have a bit easier time to analyze the data. We still have fluctuations because we get the fluctuations of the molecules in, but hey, as far as I know, nature, you get nothing for free, unfortunately. So if somebody tells you this, then you should be very careful. I think this is normally my rule of thumb, especially if it's against physics and the second law. But anyway, okay, this was just my rant over. So fundamentally, what you can see here that we can now measure the distance in time with this marker and then convert this to velocity, okay? Because we can just say, okay, we know the distance between these two molecules. We know when they show up. Again, you see that we have some problems with the filtering time here, but fundamentally, this is what you can do. And then you can do this in different methods. And if you then have some referees who ask, okay, do you really know where the end of the molecule is? And then, yeah, okay, fine, whatever. We made another marker where we have actually marked the end with the 7th marker, so we made it asymmetric. Then you know also if the molecule goes forward or backwards, you can all do this, and then you have basically 7 different time states along this molecule. So now if you plot the time that it takes for the molecule to go through, you actually see that the time is not constant between these markers, and this is actually the biggest problem why sequencing without enzymes will be very difficult, because your molecule doesn't go through in a linear fashion. Yeah, the molecule does all kinds of stuff, and if you don't ratchet it with this kind of helicase, it will be very difficult to sequence DNA, because actually in the first iteration, when you look at the first nanopore patterns, it's actually quite interesting, because there the people who patented it thought it will be all working without enzymes. Of course, it doesn't work, because exactly this is the reason, because the velocity is not constant. Okay, so if you look at here, so you can normalize this to the first marker time. So tau 1 is the first time it was between the first 2 markers. You can see that the time actually, the molecule gets slower, and then at the end gets much faster after it's translocated. Okay. So first of all, this looks interesting. What I want to emphasize here, yeah, this is of course an average over 5 different nanopores, because all our solid-state nanopores are a bit different. Yeah, so you want to make sure that you have a generic measurement here of the polymer physics and not a specific nanopore, because this can also happen if your nanopore has an impurity or some kind of thing where the molecules like to stick. This looks completely different, and the literature is full of artifacts in this way. So we want to avoid this. So we look always at several nanopores, at several things, and then these error bars are real error bars. So these are errors of the mean of the distribution. So we have thousands of events, so this is why the error bars are relatively small, and you can see within the error bars all the pores behave the same. Yeah, so all the different colors here are different pores, so it's fine. So again, this is kind of a statistical measurement with single molecule resolution, what is kind of cool, I think, because if you like statistical physics like me, this is kind of a nice tool to have. Okay, so we can really quantify the velocity change at the single molecule level. And what we see here again is that we see a slowing down and speeding up. By the way, why people didn't see this before, because we really worked hard on having a good time resolution here, yeah, because we are talking here in a noisy system, yeah, with large velocity fluctuations. To measure effects below 10% is not so easy. Okay. Anyway, so we see clearly that the molecules get slower and speed up at the end. Okay. And because we see this in several nanopores, we can claim that this is a general profile in all these kind of free translocation nanopores. If you don't see this, then you probably have a problem with your nanopore. Anyway, so now the question is, okay, why does this happen? And I already set this up. I talked first about the translocation time being much faster than the polymer relaxation time. So clearly now you go to one of the polymer physicists I know from another field, and Mugapan Mutukuma is at Amherst, and he's one of the polymer physicists in our field. And I asked him, okay, can you make an analytical model? And then he said, he's of course very clever, and he said, well, he looked at his notebook and said, I calculated a long time ago, and then he said no. However, what we can do, we can make a simulation. Okay, so what they did is they simulated our structure. So you see our nanopore at the tip. This is the channel. You see the DNA molecule, and you maybe see the blue balls in the markers, and then you can. And they set this up, and this is now to scale. And on the time scale, what you can see here, the molecules dragged through the nanopore, and what you maybe can see, the overall shape of the nanopore outside of the molecule outside of the nanopore almost doesn't change during the pulling. Yeah, I rewind this. You see here that the molecule follows a preset path when I initiate the pulling reaction, so it can't relax actually. So it doesn't do what it does during the Oxford nanopore process, where it can go through all these kind of different statistical configurations. Of course, there's shorter timescale fluctuations, but fundamentally you see that the end almost doesn't move until the molecule is actually pulled in the end, taut between this point at the end. Yeah, so just to show you, this directly leads to a different friction between the molecules that are in a different configuration. Yeah, what means you can actually use our marker molecules to tell something about the configuration of the molecule. Yeah, just to show you this, you can look at through your simulations, and they did, of course, hundreds of those, and put the molecules into different configuration. And then if you start them at the same time, you see actually that the molecule that is stretched out has a much larger friction coefficient, and it's actually faster, slower through the nanopore than the coiled up one that is close to the nanopore. I hope you see this. It's a bit too rapid, it will just rewind. You can just look at it again. But fundamentally, what you see now, part of the distribution of translocation times that we find is actually directly explained by the configurations of molecules outside of the nanopore. Okay. If you know this, of course, it also means that if you can control the shape of the molecule outside of the nanopore, you have some kind of handle to slow things down or speed things up. Okay, so while these measurements are a bit tedious sometimes and students didn't like it, in the end we learned something very profound, that that you can really do something maybe without an enzyme to slow things down and increase the resolution that you have in the system. Yeah? So the force acting on the molecule is only in the nanopore. This is why the pulling force is always the same. Yeah, and this is why it actually matters what the configuration of the molecules is another. So if you like to think about energies or energy budgets here, there's another reason to explain this. So again, to just tell you this again, so the configuration outside of the nanopore has a profound influence on how fast the molecule goes through. Okay. Again, this is one of these things that in hindsight is, of course, why should it be different? But in the end, this is hindsight bias. And anyway, it was not completely clear. So now the question is, of course, can we now use confinement to slow things down and maybe get closer to resolution of for sequencing? Yeah, because in the end, I'm a nanotechnologist, so I really like nanotechnology. So I like enzymes as well. They're amazing, but I want to get rid of them, okay? Because they limit your speed. Yeah, because normally making enzymes faster is very hard, especially base pair stepping. So now, when we looked at our nanopores, we realized, okay, of course, we have a very easy way to do this because we have this long conical nanopore, so we have this kind of confinement, so we can actually slow the molecule down by just reversing our voltage after pulling it in. We can just make it much slower when you go backward, okay? This is exactly what happens. So what we can do is we can pull one molecule through, and then reverse the voltage directly after and pull it back, and then what you see here, you have 1, 2, 3, 4, 5, 6 markers going in roughly about half a millisecond, in 1 millisecond, and if you pull it out, it's actually much, much slower. And why is it slower? Because A, there's more friction, yeah, and the molecule is more stretched out when it's coming out in the system. But you also directly see, of course, the disadvantage of this is because friction is more important, you actually see that you actually have larger velocity fluctuations, yeah? So again, you get nothing for free, but anyway, hey, at least we can slow it down. Great, so now what can you do with this? Yeah, because fundamentally, remember, what we want to do is we want to identify molecules. And of course, if we want to identify molecules, the resolution along the molecule is kind of important because the more marker you can measure, the more molecules you can distinguish. Yeah? So now you can ask the question, so what is actually the resolution of our nanopore sensors? And if you look at this data, actually, this is almost also 10 years old now, we already noticed that there's some kind of fluctuation in some of these peaks, okay? So now what you can do is you can really have a patient postdoc and make this pore as small as possible. And then we actually do some modeling with finite element calculation and see what is really the resolution of our nanopore, yeah? What is limiting us? Is it limiting the speed of the nanopore? Is it our filtering times? Does it have actually the possibility to distinguish between bases? So what's going on there? So and again, if you do this finite element model, you can actually make a model where you model your DNA molecule with these two structures that would be our labels next to each other, and then you pass it slowly through the nanopore. To cut the long story short, if you pass it through the nanopore infinitely slow, this is exactly what Oxford Nanopore does, yes, slowing it down, then you actually can see that in each of these events, you always see these two markers, even if they are only a few nanometers apart, even in a large nanopore. So we are only limited by our time resolution of our measurements. The information about the structure of these molecules is there, and we in principle have really sub 10 nanometer resolution in all of our nanopore measurements. The question is only, can we measure it, okay? So now if you make a nanopore, and again, it's not so easy to make a 3 nanometer nanopore in glass, but it's possible. So now if you pass these molecules through, you can actually see here, yeah, so these are two peaks that so this is a full molecule going through at a rate of 0.4 base per microsecond, still 1,000 times faster than 250 times faster than Oxford Nanopore on average. And now the molecules that we have two groups of markers here. These are dumbbells, just DNA structures, doesn't matter what it is. Yeah, so they have a distance of 76 base pairs and are each spaced 18 apart. So there are 4 markers, okay? If you now look at it on large scale, you actually see that you see these two peaks that are these two groups of markers. If you now zoom in, what you actually see here, yeah, you see two nice space peaks, so 4 peaks here, so you really have this resolution of a few. We could claim 18 base pairs. It's kind of 6 nanometers. It's pretty good, yeah. So this also allows you to do really high resolution measurements. Looking at the time, I just want to mention one last thing because I know that this is some interest. So because now, of course, we have this method to look at DNA structure quite well. Yeah, so we understand our DNA nanopore microscope quite well, so now we can try to do some more fancy things with it, let's say. Yeah? And one fundamental problem is always to detect modifications along DNA molecules and RNA molecules. Now I want to tell you one more idea how we can make one additional trick to actually even query the sequence modifications on DNA molecules. Okay. So it's a bit complicated, but bear with me. Okay, so now what we do is we use a hybridization pattern to look at DNA sequences with sequence resolution. Again, it's not for sequencing, it's for a certain query. Yeah, so for instance, if you have a certain TB, tuberculosis infection, you want to directly know is it antibiotic resistance or not. Yeah, so this is normally given an information that for what you have to read one single base pair in a long DNA molecule. You don't need to sequence the whole DNA for this. You just have to ask about one certain position. Yeah? And what we do for this is the following. Yeah? We target a position along a DNA molecule that can be in here. Okay, and what we do is we make a loop that is easy for us to read. Okay, we are using now DNA nanotechnology. The nanopore is just the readout in the end. Yeah. So what we do is we use DNA nanotechnology to actually pull things together and read out these kind of systems. Yeah. So we call this DNA nanolatch. This is Yunshin's work. Is now actually in review in a paper. Now it's not just submitted. So basically the idea is the following. So you take a DNA molecule, you then use it to pull a loop into the DNA, and then if one of these molecular arms if one of these binding sites has a mismatched base pair, it will not form. Okay, this is how it looks. So this is a target DNA molecule. This could be an RNA molecule from as I said, tuberculosis bug. And then if the molecule is there, you get this large peak here, yeah, because you make this loop and we read it out in the nanopore. You can also query several sites, and then you can actually detect sequence mismatches in these systems. Yeah, just to show you quickly, it's just how this works. Yeah, again, we target something in this kind of site here with our loop system. Yeah, so we make this loop only if the sequence is a perfect match. Okay, so what you can see, this is a positive event rate. So the number of loops you find, depending on the sequence, you see that. For the perfect match, we get around 50% of the molecules are folded. And again, this is of course thresholding problems. And again, this could be improved by better data readout. And then you see with the other ones where you have non-perfect matches, you actually see a much lower ratio. And this can actually be also used to detect methylations. Yeah, because we also see a subtle difference in the methylation pattern in these systems. Looking at the time, and don't want to keep you from lunch. I just want to go to the conclusion. So I told you about a story about how you can use DNA nanotechnology to enhance nanopore sensing. This is solid-state nanopore sensing. Again, we don't use enzymes here for this type of work. I didn't talk about the supercoils and glass nanopores. This is another thing that can be problematic, but of course you can use this technology, and this is what we also did during the COVID pandemic. Detect RNA, DNA, viruses, bacteria, whatever, fungi, whatever you want. Yeah, and the outlook is, again, quite far-ranging. And again, the fundamental thing why I'm interested here is because we have a classification problem, because what we need to know, which molecule is this? Yeah, is it 5 peaks, 6 peaks? Which classification is this? And with this, I would like to thank you for your attention.
Comments? Yeah.
Obviously, the data produced depend on the membrane and the shape of the hole. Did you look at different shapes and different membrane?
Yes. Okay. So let me just go back. So I glanced over this. So these measurements, if you look careful at these events, these were done in membrane nanopores, so short nanopores, so 20 nanometers in membrane thickness. Okay, so these don't have this kind of channel in the system. And then if you look at this, we also looked at this with our conical nanopores. There are these channels, and you see the same pattern. Kind of subtle differences, but this all will depend anyway on the exact size of the nanopores and the voltage you apply. But you always see this kind of relaxation pattern and fast speed up at the end. So these kind of polymer physics, if your nanopore is behaving well, meaning you don't get sticking or some other things, interactions with the nanopore, you can, this is a generic process, if that answers your question. The other thing is, I didn't talk about folding now, okay? We can look at folding, so maybe I can show you. So one of the things that I didn't talk about, I had planned this, but since you asked, so one problem is that, of course, DNA can have knots, okay? You also can study knots, because one of the biggest problems for us is, unfortunately, as you know, if you have long pieces of string lying on the ground, it can self-knot anything, and this is things that we need to deal with as well, yeah? If you look at some of our plots very carefully, we have always a small positive false positive rate, and this is exactly because of knots in the DNA. I mean, you can deal with it, but yeah, this is something that we can see also in the nanopore. So if you're interested in these things, I'm also happy to talk about it later. But we can see all these kind of topological structures in the system.
These sort of fast, reduced ways of reading it, what is their power consumption compared with, say, the ultra nanopore?
Okay, I never thought about it in that way. Yes, so I know from cost it's a bit cheaper because we don't have enzymes, okay? You still have to make the solid-state nanopores, okay? So this is why it's a subtle question, but maybe I should think about it, how efficient it is. But since it's 1,000 times faster, it should also be a bit more energy efficient, yeah? Because we have but again, this has to be, it's probably a subtle calculation.
I think that's quite relevant to being able to use these things in the field.
Yes, yeah, no, I agree. Yes, this is all driven by cost. Yes, so also if we look at low income country applications, and then it's all running costs. It's not buying the machine; it's actually the running. It's the important thing. So I fully agree with this. I never thought about it in that way. I only looked at it as an economic cost, but not energy. Yes, thank you. Nice question.
Okay, so if there are no other comments or questions, let's thank the speaker again, and let's thank all the speakers this morning.